Merhaba hocam, iyi günler. This is the video for explaining this simulation and its components. Let's begin with the overall system setup. Our simulation includes two base stations, which is GMB1 and GMB2 here, and two MEC hosts, MEChost 1 and 2, and three mobile user devices called UEs, these three, and one MEC orchestrator, which is responsible for managing application placement, and a signaling proxy called UALCMP here, short for User Application Lifecycle Management Proxy. And first I will explain the components, then we'll pass to the actual simulation. So first we have a G-Node piece, GMB1 and GMB2. These G-Node Bs are 5G base stations. Their job is to provide radio access for user devices and act as a gateways to the core network. In our simulation, each user device initially connects to the closest GMB and may switch during movement. In the simulation, these devices will move from right to left, from GMB2 to GMB1, and this movement is called handover. And the GMBs are connected to UPF and also exchange control information with each other via the X2 interface. This X2 interface is a logical communication link between two neighboring base stations, these two. Specifically in 4G simulations, it's between E-Node piece, and in here in 5G, its equivalent is between a G-Node piece, and it's functionally for handover management and user device connect transfer, load balancing, and intercell interference coordination. I can show from the figure we have. Here, X2 from UEs, from device apps to user apps. Here we have X2 interface in the architecture. So let's pass to the user devices. There are three of them. These UEs, or user equipments, represent devices like smartphones or sensors. Each user device starts at time 1 second and sends an application request to make infrastructure. These user equipments use the UE warning app alert, UE warning alert app, which is a delay sensitive MEC app, and these user devices move using linear mobility, which simulates real user motion, and this is also triggers handovers as they pass between zones. These base stations have zones. Since these devices moving, they will leave GMB2 zone and enters the GMB1. And the another component is MEChost. There are two of them. They are edge computing servers where applications are deployed. In the simulations, MEChost 1 has more CPU power, while MEChost 2 offers the required servers in the location service. And this location service is a type of MEC multi-access edge computing service that provides real-time location information of user equipments to MEC applications. It allows MEC applications to query the current position, for example, X and Y coordinates of a user device. And despite having a lower CPU capacity, MEChost 2 is always selected in the best case due to our policy logic. And each MEC host includes virtualization infrastructure management, VIM, to check resource availability, and a MEC platform manager to handle application installation. And the other component is the MEC orchestrator. And this is the brain of our MEC system. In the orchestrator receives app requests, evaluates them, and decides where to launch the MEC app. In this best case scenario, it will always select the MEChost 2 based on our custom policy. And the orchestrator selects a host via find best MEChost function and sends a instantiation message to the appropriate MEC hosts. And we have here UALCMP, stands for User App Lifecycle Management Proxy. It acts as a middle layer between user device and the orchestrator, because our signal will come from here to IUPF2 and to the center UPF to here, and it will send acknowledgement and also communicate with the MAC orchestrator. And the other components are UPF and its components 1 and 2. And UPF, or user plane function, is a core part of 5G architecture. It handles actual user data, forwarding packet between GMBs and application servers like Mac. In our simulation, UPF is the central unit, and IUPF1 and IUPF2 are connected to the each GMBs. When the user device sends data, it flows through to UA and GMB to IUPF and MultiMEChost. And the UPF ensures the traffic is routed to the correct application endpoint. And we have here, for example, binder. The binder is Simu5G's internal tracking and management service. It keeps track for GTP tunnels, user device sessions, and resource mappings. It helps coordinate routing and mobility, especially when handovers occur, or handovers occur here, or MAC-apps need to communicate. And we have carrier aggregation. It's a shared component that defines the available frequency bands and bandwidth. It helps simulate realistic channel conditions for the user devices. And in this scenario, it's configured with 2 GHz carrier and 50 resource blocks. And we have IPv4 configurator here. And this module automatically assigns IP addresses to every device in our network. It ensures that communication between user device, GMB, UPF, and MultiMEChost works without manual addressing. And we have routing recorder, and it's disabled in this case. And normally, this module records IP routing paths for debugging. However, we have disabled it in best case to simplify simulation and reduce overhead. And you can re-enable it in more complex scenarios where IP level debugging is needed. To summarize these components, these user devices move and generate MAC requests, and this UAL CMP sends these to the MAC orchestrator, and the orchestrator uses a custom policy to choose MultiMEChost2 always, and applications are instantiate successfully without errors, and all communication flows through GMBs, user devices, GMBs, UPFs, and the configured network backbone. This is it for the explaining the components. We will go through for the understanding and explaining the simulation logic. In this section, I will walk through the implementation and analysis of the MultiMEChost simulation. Before diving into the simulation, let me first explain the background. In 5G networks, multi-access edge computing, or MAC, brings computational resources closer to the users. MAC orchestration is a decision process of selecting the right MAC host to deploy applications. This is critical because poor selection leads to increased latency, CPU bottlenecks, or service unavailability. Our goal is to create a smarter selection strategy. Now let's walk through what's happening during the simulation step by step based on what we observe in Qt simulation. This is here visually. So first, let me open. As soon as I start, because of I start very fast, before this inet messages, there is a find interface by name. It's used by components to resolve network interfaces. And there are handover frame events, initialize handover handling logic for the user devices. And components like GMBs, UPFs, and user devices are triggered and initialized before this packet inet messages. And here we are starting to X2 interface installation between GMBs. This messages like packet inet, cookie echo, and cookie egg are part of the CSTP handshake between GMB1 and GMB2 to establish the X2 interface. And this SCTP handshake is a stream control transmission protocol. It has initial four-step process used to establish a reliable connection between two systems over SCTP protocol, similar to TCP three-way handshake, but more secure and robust, used for control signaling between core and access network components. And it provides reliable message delivery, order streams, and stronger protection against those attacks. And here, at first, we have init message from client to server. It starts SCTP connection like TCP SYN, and after that, it will send the acknowledgement. It's from the server to client. It acknowledges and responds with setup info, and then it will send a cookie echo from client to server. It confirms client's agreement to setup, and after that it will send the acknowledgement message from cookie echo from server to client. It's a final confirmation, and association established after this. And here it is. And here we have TTI tick and HARC feedback messages. First, here we can see, but there is a TTI tick self messages at GMB2 represent a regular 1 millisecond time slot in 5G from a transmission time interval. And these are HARC feedbacks from user devices, confirm reception of transport blocks and triggers resource grants. And after that, we have a packet SYN message from a user device GMB forwarded through IUPF2 and UPF to UAL CMP start TCP connections. And here, after this SYN packet is sent, and UAL CMP replies with a SYN-ACK message. And this flows back to user device via same path. After that, we have followed with the, let's wait for it. Yes, TCP ACK message. And these are the completing the TCP three-way handshake with this. And after that, like you said, we have handover movement. This handover with this user devices begin moving from right to left from GMB2 to GMB1. As each user device exists in GMB's coverage and enters GMB1's area, and here a handover frame is triggered. And this involves cellular logic in GMB1 and GMB2 also, and updates user device to GMB associate connections. And after this, we have TCP sec messages, packets flow in both directions from user devices GMB and UPF2 and UPF and UAL CMP and reverse, and this will occurs 3 times. We have acknowledgement, and again we have TCP send message from the user, but it was the first time, and it is the second time, and it is the third time. And this is the acknowledgement from that to that. And again. Like here, I was waiting for this, and here around 1 second, User devices send a request to UAL CMP, and UAL CMP forwards create context app message to make orchestrator 3 times, and the orchestrator chooses MultiMEChost2 hard-coded in best case and sends back acknowledgement like here. It creates context app message. And these are the first loop, and the other loops the same with this. This happen, and the start of this loop is the handover moment. And when I speed it, like handover, and these messages sending in each loop. After handover, it's repeating, and in each handover, data continues following via updated GMB and UPF paths, and this continues until simulation ends at the 60 seconds. And on screen, we will see the user devices move leftward, and the user device that at the 0 index reaches GMB1 first and switches connections. And the visual lines indicate radio and core network flows updating dynamically. And once these at this one device get off of the area of the GMB2 and enters the GMB1, we will see now this path will occur for this one. Like here. And the summary of this, each message and a flow serves a critical role here. SYN, SYNAC, and ACK messages sets up reliable transport between user devices and Mac app, and TCP SEC and TCP ACK messages represent a data flow from apps and feedback. And the create context app message from Mac orchestrator to UAL CMP is the core of Mac app deployment, and the handover frames enables mobility and dynamic coverage handling, and the self messages like TTI tick and feedback drive simulation time and scheduling. These interactions collectively simulate a realistic and responsive 5G Mac deploy scenario. And at the 60-second mark, the simulation concludes. All user devices have requested and used Mac services, experienced at least one handover, and the system behavior remained consistent. And so this was it for explaining simulation and its components.